I normally dislike combinatorics problems a lot. I don't know why. It's just the way I am, I suppose. But this one wasn't that bad, I guess. It reads that a square board with sides of length 8 centimeters is divided into 64 squares, with each side being 1 centimeter. And each box can be painted white or black. And we gotta find the total number of ways to color the board so that each square of side 2 centimeters formed by 4 squares with a common vertex contains 2 white and 2 black squares. So just a very standard combinatorics problem. How many ways can you do a type of thing? Let's kind of do an illustration, because for this kind of problem, of course, an illustration is very much useful. Okay, this is my very beautiful board, a very beautiful table here. 8x8 table, basically. And we gotta make it so that in each of these 2x2 squares, so one of these, it has to have 2 black and 2 white. It can be something like this, maybe like this, maybe like this. There's a couple of different ways to fill a 2x2 square. I think it's like 6 ways in this manner. So we basically gotta find a way to fill out this whole square with that given constraint that every single 2x2 square needs to have exactly 2 white cells and 2 black cells. My approach to this problem was basically work through it row by row. And the moment you go through the first row, the problem just kind of solves itself in a way. You'll see what I mean in a moment. So let's take one row. Let's take this top row, and the amount of ways we can fill up this row with black or white cells, it's 2 to the 8, because there are 2 ways to fill out this cell, 2 ways to fill out this cell, and so on and so forth. So 2 to the 8 ways to color this row. And now we're gonna assume that there are at least 2 cells of the same color adjacent to each other. So for example, we might have 2 black cells next to each other, or we might have 2 white cells next to each other, like so. And in this way, I kind of want to draw an example so you kind of get what I mean. If we, for example, have 2 black cells here, and maybe another black cell here, this is an example. Immediately, if we consider the 2x2 square that has these 2 black cells, we already know that these 2 cells directly below the 2 black cells need to be white, because else we can't make that arrangement. That doesn't work. If we have a black cell here, then we can't do that. So these need to be white. And if these are white, then these have to be black. And then these have to be white, and so on. So the moment we have 2 adjacent cells, or at least 2 adjacent cells, because, for example, if we were to have 3, then it also applies to this entire rest of the column. So what I mean here is that for the first row, to have at least 2 adjacent cells, the cells directly below the cells that are adjacent must be the opposite color of those, and then we continue so on and so forth for those specific columns that have the adjacent cells. But what happens to the other columns? Because, for example, in this case, we have these that are already decided. They're gonna be in a sort of zebra manner, like black and white, black and white, black and white, or adversely, white, black, white, black, white, black. So for the other columns, you can actually kind of form a similar argument, because instead of considering this square or this square, which we previously considered, now we're going to consider this square, because this cell is black and this cell is white and this cell is white. We have to have this cell black. And in a similar fashion, we can basically fill out the remaining rest of this second row, because we already set the first row in a certain manner. And of course, this is one specific example, but this can apply to any that has at least two adjacent cells of the same color. So once we have two adjacent cells of the same color, the second row is already going to have only one permutation, only one arrangement, and so on. We can make the same argument for each row, and we can basically fill the entire grid in one specific way. So this is what I'm trying to say. If the first row has at least two adjacent cells of the same color, then the remaining rest of the cells can only be colored in one specific arrangement. So if there are two to the 8 ways to color this row, then there'd be 2 to the 8 possible ways to arrange the grid, is what I would say, but we haven't considered one other case. Let's write this down though, because in total there'd be 2 to the 8 ways to fill out the grid, but there are two cases where there are no cells next to each other of the same color, which would be this, black, white, black, white, black, white, black, white, or adversely this, white, black, white, black, white, black, white, black. So these are two specific cases that don't fall under this idea. So we got to consider them separately. But we already have a big number of cases, and these are only two cases. These are only two cases that don't really take that long, because they're sort of the same thing. We were to have black, white, black, white, black, white, black, white, without loss of generality, because it's going to give the same outcome if it's white, black, white, black, white, black. This entire row can also be either black, white, black, white, black, white, black, white, or white, black, white, black, white, black, white, black. Because if you take this square, it can be black here or black here, and it'd be okay because it's only either here or here because of the zebra pattern that we're establishing. So because of this, the second row is either going to be this or this. So there's two ways to do the first row, two ways to do the second row, and then we just apply the same reasoning to the remaining rows. We have two ways to color this, two ways to color this, two ways to color this, two ways, and two ways. In total, there'd be 2 to the 8 more ways, because there are 8 rows, 2 ways to color each row. And so in total, since we've already considered all the cases, there'd be 2 to the 8 times 2 minus 2, which is 512 minus 2, which is 510. So there'd be 510 ways to color the square board in this manner. And that's basically the entire problem. Of course, when you want to write down the actual proof, it does take longer. This video was kind of short because I mostly just went under more so like through the thought process of the problem and not more so the proof. That was kind of like a different approach compared to some of my other videos. So if you do prefer a more proof-based approach, please let me know. But I hope you did enjoy and did understand. Normally, again, as I said in the beginning, I don't really like combinatorics problem that much. But this one was pretty simple. probably why I like them more than brothers. I hope you enjoyed. I hope you learned something new. Please, if you have any doubts, any comments, any feedback, please let me know in the comments down below. And I hope you enjoyed. That's it. Bye bye.